and welcome to NPTEL course on fiber optic communication systems and techniques. This is our second module and this is the module where we actually begin the study of fiber optic communication systems. In the last module, you might have seen the system of fiber optic communications as it would look today, and you would have seen that there are a lot of elements in that, right. But the basic fact is that information in an optical fiber is conveyed by transmitting light and modulating one of the properties of the light. Okay. So, how exactly do we generate light is the subject of lasers and LEDs, to which we will come sometime later in the course, but how do we actually describe light first of all is the topic that we would consider now. This is important because understanding the properties of light or light waves, as you would shortly see, is critical to understand the behavior of light inside an optical fiber. Okay. So, with that in mind, let us actually start our study of fiber optic communication systems by looking at optical fibers itself. So, once we understand the fibers, we then go and understand the sources, light sources, that is lasers and LEDs, and once we understand lasers and LEDs, then we go and understand the detectors, and once we have all these three basic components of a optical communication system or a fiber optic communication system understood, then we will study how to modulate, how to efficiently transmit light. If there are problems in fiber transmission, that is light as it propagates through the fiber, what are we supposed to do to overcome those problems and make our communication systems better in terms of very high data rate, very low bit error rate. Okay. Let me begin by recapitulating something that you already know of. Light of course can be modeled in many different ways, and I am using the word model because no one really knows exactly what light is. You have certain physical phenomena and then you develop your own understanding of that physical phenomena by abstract means, which we call as models. For example, you must all know Ohm's law. You have a resistor, and then if you apply a certain voltage across this resistor, then there will be a certain current through it, right. And you must have done many experiments, but if you actually look at a resistor, you will see that it is a physical piece of device, right. And what you have captured is mathematically the relationship between the voltage, current and the resistance that this particular resistor is offering. So, you would never understand, or you do not want to complicate your understanding by knowing exactly what material this resistor is made out of, how exactly is this resistor connected, and how is it that someone has guaranteed that this resistor gives you say 20 kilo ohms of resistance, right. So, those are the finer details to which you do not want to get into, it perhaps does not serve your purpose, but to understand this resistor and its behavior in circuits, it is enough to understand Ohm's law. So, what you have is a physical device, and what you use to understand what is going on when you connect multiple such resistors is the abstract model of the resistors. So, much in the same way you can think of light and various phenomena that involves light, right. So, you take light, pass it through a lens, you take light and then pass it through a cavity, or you take light and then reflect it off of a mirror. Then light, you take two different kind of light sources, or you take the same light source and split it into two parts and then make them interfere with each other. These are all the phenomena which involves light, and depending on the phenomena that is involved and the simplicity of the explanations that are required, you can think of light as rays. So, when you take a piece of pen like this and then take a piece of or you take a bucket of water, immerse this piece of immerse this pen inside the water, to describe what happens, what you see, that the pen appears to be bent, right. You do not want to include lot of details, you can think of and arrive at conclusions which are basically correct by treating light as rays. But there are situations where you cannot just treat light as rays. So, this actually happens when you start thinking about light propagation inside an optical fiber. Okay. There you need much more sophisticated model, which we call as electromagnetic model of light. So, what we claim is that light is an electromagnetic wave, and electromagnetic waves are studied by means of certain equations and certain theory known as electromagnetic theory, and these equations which describe electromagnetic theory are due to Maxwell and many other researchers in electromagnetics, and we use Maxwell's theory of electromagnetic waves to understand light. Please remember that this electromagnetic theory can explain many phenomena which involves light, where light appears to act like a wave. Okay. However, there are phenomena where light appears to act like a particle, for example, in the photoelectric effect, which we would not really be able to treat it, okay, when we think of it as an electromagnetic wave. So, there are cases where you handle light as a wave, handle light as a ray, and then handle light as a particle or particle like behavior called as photon behavior, and that goes to the quantum theory of light. So, you have these different models, not because you are just interested in coming up with different models. These models serve the purpose of explaining the observed phenomena in the most appropriate way. Okay. So, having said that, we now go on to electromagnetic theory. I will not describe electromagnetic theory from the first principles. I assume that you have all done a course on electromagnetic theory in your earlier semesters, and we will use only some of the aspects of that electromagnetic theory. Do not worry, we are not going to use Coulomb's law, we are not going to use we are not going to solve problems using Coulomb's law or Biot-Savart's law or anything like that. We stick to reasonably basic electromagnetics that we need, and most of this electromagnetics happens to be use of Maxwell's equations and manipulation of these Maxwell's equations, as you will see. Okay. So, having said that, what are Maxwell's equations? These Maxwell's equations describe almost every known property of electromagnetic waves, right from DC, that is 0 frequency, all the way to optical frequencies. Just for the record, optical frequencies are in the range of terahertz and more, whereas microwave electromagnetic waves are in the range of few gigahertz, 10 to few gigahertz of range, and then there are of course various other frequencies which are important, and this entire thing is called as the electromagnetic spectrum, okay, of which optical is at the higher frequency range, and those are the things that we are quite interested in. And it is interesting that all of this phenomena, which is at a wide frequency scale, is described by a very few equations supported by certain material properties. There are 4 equations traditionally known as Maxwell's equations, and couple of additional equations describe the properties of the materials, and these 4 equations connect 4 electromagnetic quantities. What are those electromagnetic quantities? You have what is called as the electric field intensity, and you can see that after writing electric field E, which is denoted by the symbol E, I have put a bar over here. This bar indicates that this is a vector quantity. Okay. This is my notation of using a vector. You might see people using different notations. For example, writing an arrow is considered another equivalent way of talking about a vector. Some books or some literature uses an underbar to denote a vector. These are all equivalent representations, and these vectors are of course very different from scalars in the sense that vectors have direction. So, these electromagnetic waves which I use by putting a bar overhead is what is called as a vector, and it has of course direction, and this electric field vector or electric field intensity actually can depend on the various it can be different at various points. Therefore, we generally denote them of course after choosing a certain coordinate system. In this case, I have chosen the Cartesian coordinate system, which has 3 perpendicular axes. You know this very well, these are the x, y and z axis, and this is the so called right handed coordinate system, in the sense that if you rotate from x to y your fingers, the thumb finger would actually point along the z direction. Okay. So, this electric field intensity or electric field, as we would call it for short, depends not only on the space or at points x, y, z, it also in general depends on time. Of course, when it does not depend on time, you go to what is called as electrostatic phenomena, but when it is dependent on time, you go to what is called as an electrodynamic. You see, static, time equal to, or it is independent of time, dynamic where things change with time. So, these are dynamic field quantities, and we use a shorthand notation instead of writing x, y, z. We use a shorthand notation to denote this by a vector point r. Okay. R is the position vector of space. So, for example, if this is r, then this is the position vector drawn from the origin. The distance from the origin to the point here will be the length of this vector, okay, and this is the position vector that we can specify. So, any point, every point can actually be thought of as being connected to the origin through a line, okay, of appropriate length, and therefore, you can write electric field in as a function of these points where we are using this vector notation. So, these are the position vectors, and then you are talking about this position vector and time dependent field quantity. Okay. So, Maxwell's equations do not only talk about electric fields, you also have what is called as a displacement or electric flux density vector. Even this flux density vector is dependent on both r and t. Then you have the magnetic field quantities, which are B, the magnetic flux density sometimes it is called, or magnetic field it is called in some texts. So, it does not matter what it is. So, we denote them by the letter B, and then you have magnetic field intensity, which we denote by H. Okay. So, in my ordinary usage I will call this as electric field, just to simplify, instead of talking every time that this is electric field intensity, I will just call this as electric field. Similarly, I will call H as magnetic field. Okay. Please note that all these field quantities are dependent both on position as well as on time. So, in general they are time and space varying quantities, they vary with space, they vary with time. Okay. So, how are these equations connected, how are these quantities connected? Well, one of the laws which is originally due to Faraday tells you that the time rate of magnetic field is the reason why you actually have an electromotive force, or it induces an electromotive force. So, if you take a certain experimental situation where the magnetic flux density which is obtained by integrating this B over whatever the area, and if this magnetic flux is changing with respect to time, right, then that induces certain EMF in the electric wire that it would be there. So, the exact details of these equations I am assuming that you would have read in electromagnetics courses, therefore, I am not showing you, I am not going into a lot of details here. The objective is to just write down Maxwell's equation and point to a couple of interesting important relationships, and then move on to consider the manipulation of these equations. Okay. So, I am not going to the physical experiments which led to these equations. I am hoping that you would have done all that in the electromagnetic theory courses earlier. Okay. So, this equation which was originally due to Faraday is called as Maxwell-Faraday law or Faraday's law, just for simplicity. Okay. And the form that I have used is what is called as the differential form. So, in the differential form of writing, you have these operators which are called as point operators, and the special symbol which is inverted triangle is what I call as a del operator. Okay. So, this is an operator, and this particular cross is denoting what is called as a curl. Okay. The corresponding integral version of this law, which in some sense is much more general, goes something like this. You have an electric field integrated over the length or the closed loop, which for example could be made out of a simple wire. Okay. So, the closed loopness is indicated by this integral, by this circle symbol on the integral. Okay. And whatever the quantity that you have E dot dl inside, from when you integrate it over, is what is called as the EMF, and sometimes this EMF is denoted by this particular letter nu. Okay. So, this denotes an EMF over the entire loop. In the static case, when there are no magnetic fields involved, this EMF over the entire loop will be equal to 0. This is your familiar KVL equation. Okay. So, there are no sources, magnetic field is not changing, and then as you pass along the loop, you would see that the total EMF induced would be 0. So, there might be some elements where the EMF is increasing, but there will be some elements where the EMF will be decreasing, with the net result that in the static condition the EMF will be equal to 0, but not so when there is a magnetic flux. So, for example, if this is a wire, okay, I will just put the dot two ends to measure the EMF here, if there are magnetic flux lines which are changing with respect to time, okay, then this changing magnetic field or changing magnetic flux induces a non-zero EMF, and the amount of that induced is given by this particular equation. So, this is the change in magnetic flux. So, this around the loop will be dl, and the area that this is covering, the wire or the mesh is covering or the loop is covering, is the surface area ds. Okay. So, when you integrate the magnetic field over that surface, you will get the flux, and the time rate of change of this flux, the negative time rate of change of this flux is the amount of EMF induced, and this minus sign comes because what is called as Lenz's law. Okay. So, please refer to electromagnetic theory courses to get a better understanding of these equations. Okay. So, we will now write only the differential forms, the integral forms. You can look at the textbooks, and then you will be able to write them out. So, that was one equation which connected E and B. So, E connected to B via Faraday. Okay. What is the other equation? So, consider del cross H, the same curl operation, but now performed on the magnetic field H. Before Maxwell, this was equal to J, where J is called as the current density. So, if you have a source of current, producing a battery, for example, connected to a wire, producing this current, then there is a certain current density. Okay. So, before Maxwell came to understand all these things, this was known as Ampere's law. Ampere's law connects H to J before Maxwell. Okay. So, this was Ampere, but what Maxwell observed after looking at these equations are that these equations are not consistent with what comes out from these relationships. So, he added a term to make it consistent and called that term as displacement current. Okay. So, he called this as displacement current, or this is displacement current density. This kind of completes the current law. For example, what it means is that you might have a regular conduction current density J, but when you connect a capacitor, clearly there are no free electrons inside this capacitor, right. So, how would current then continue? So, if you try and apply KCL to this node, then KCL seems to fail because there is an incoming current, but there is no outgoing current. But what Maxwell did is that he said it cannot happen that way. There is current beyond this, or there is current in the capacitor, and that current is what we call as displacement current, which is given by del D by del T. So, I hope you are able to see all these things, and what Maxwell did to complete Ampere's law is now called as Ampere-Maxwell law. Okay. And you can see that Ampere-Maxwell law connects H with J and D. There are two additional laws known as Gauss's law for electric fields and Gauss's law for magnetic field. Gauss's law for magnetic field tells you that divergence of B is equal to 0. Now, divergence is denoted by del dot. Okay. So, this dot denotes divergence, and divergence of B equal to 0 simply means that there are no sources or sinks to magnetic field lines, right. And the same case for electric field tells you that in general in matter it is a D field that you need to consider, and divergence of that D field is equal to whatever the volume charge that is enclosed by the region. So, you can see this picture out there, rho v corresponds to volume charge density. So, these are all the density quantities because we are considering the differential form. So, what it means is that if I actually have a positive charge, right, then electric field vectors all come out of this. So, the electric field vectors are, so it does not have to be a single positive charge, it could be positive, it could be charge density, but if it is positive, then the electric field lines or the D field lines actually come out of this particular charge region, right. And then when you enclose this certain region around this and then evaluate the divergence of D, then it will tell you exactly the amount of charge that is enclosed. Of course, there are certain mathematical difficulties which I am pretty sure you must have studied them in electromagnetic theory. If not, you can go back to that, but these equations are actually quite valid. Okay. and what it says is that it is not just that del dot D is equal to rho v acting like positive charges having the sources. If you have negative charge region, okay, a region which is negatively charged, then electric field lines can actually terminate on that, right. So, in one case you have a convergence of field lines and in one case you have a divergence of field lines. If you think of convergence as negative divergence, then one equation itself is sufficient. To denote divergence you use a positive value, denote convergence you use a negative value. So, del dot D equals rho v when rho v is positive means that electric field lines are all diverging away from a particular region which encloses the charge, and when del dot D is equal to minus rho v, then it means that field lines are all converging to a particular point, okay, or to the region where that is charges are enclosed. So, you have divergence and then you have convergence. What Gauss's law for magnetic field tells you is that there are no magnetic charges, because if there were magnetic charges it would be possible for us to actually put a magnetic charge and have the magnetic field lines come out of that, and put a negative charge and then have magnetic field lines come into it, right. But there are no positive magnetic charges, or sometimes called as north pole separately and south pole separately. So, I do not have an ability to separate a north pole from south pole. Okay. So, in that cases the field lines are always going to be continuous, right. So, the field lines are never going to have a point where they are starting and where they are converging. So, these field lines are all continuous, and if these field lines originally were 0 at some point in time, then they will actually turn out to be 0 at all the times. In fact, their divergence turns out to be 0 all the time. So, these are the 4 Maxwell's equations which are very important, which we will use in order to study whatever the light propagation inside the fiber and other optical elements. Okay, we have so far been talking about these vectors. Obviously, the knowledge of J and rho v needs to be known. These are what are called as source vectors and source charge density, because unless someone gives me the current distribution or the charge distribution which act as the sources to generate E, H, B and D, I will not be able to solve these equations. But there are situations where these field quantities may be taken to be 0. So, for example, think of this: you have an antenna, okay, where there is a certain current distribution, and this current distribution when it is changing with time can give rise to changing electric field and magnetic field, right. And because the medium is free space, I am assuming the medium to be free space, there is no real distinction between D and E, right, and no distinction between B and H. I will come to that in a moment, but we can just get away by using 2 vectors E and H to describe the entire system out there in free space, right. So, you have an antenna where currents are changing, and this changing current distribution creates a changing electric field and magnetic field which then radiates away, right. And then now you imagine that you are far away from the antenna and you have a receiving antenna over there. So, in the receiving antenna, you have this antenna pointed to the region where there are these radiating fields, and some of that fields can be intercepted by the receiving antenna and collected. Okay. There in between region there are no currents, right. So, if you want to describe the propagation of electric field and magnetic field, the radiating electric and magnetic field in the region between the 2 transmitters, I mean between the 2 antennas, there is no J and rho v there, right. But these J and rho v are required at the transmitter side, at the transmitter antenna side, to actually generate E and H. Now, when it comes to the receiver side, the receiver has intercepted some of the radiating fields, and that electric and magnetic fields that impinge on the receiving antenna create the current distribution. Okay. So, current distribution is necessary to create E and H, and E and H once at the receiving antenna create a current distribution, of course not the same current distribution, but an equivalent current distribution, so that you can then understand what happens to the fields converted back into the current. Okay. So, but there are regions in between where J is 0, rho v is 0. A very similar situation occurs in an optical fiber as well. So, I will have a source, okay. So, maybe a laser or something, I couple light into the optical fiber, but inside the optical fiber I do not have any J or any rho. I do not place any magnetic, I mean I do not place any electric charge in there, nor do I place the current density. I do not put a wire in the optical fiber and then connect that wire to a potential source. Okay. So, inside the optical fiber I can assume that both j and rho v can be equal to 0. Rho v corresponds of course to only free charges, j corresponds to the current density. Okay. So, let me collect all these Maxwell's equations for you. One is del cross E equals minus del B by del T, then you have del cross H equals J, which I will assume to be 0 because I am interested in considering the situation where there are no free charges and there are no free currents. Of course, they have to be there at some point in the space because they are the ones which generate E and H and additional fields. Okay. And then I have del dot B. So, I have del dot B equals 0 and then I also assumed del dot D equal to 0. In general, D and E are related by the material properties. If it is free space, then D is equal to epsilon 0 times E. This is called as epsilon 0 or epsilon naught, and this is the permittivity of the medium. Permittivity of the medium tells you how susceptible the medium is to the electric fields. If it is easily susceptible, then the permittivity will be very high, but epsilon naught is the permittivity of vacuum. Okay. In the material medium, you can rewrite this one as epsilon 0 epsilon r E, where epsilon r is called as the relative permittivity, relative referring to vacuum. Okay. There are more detailed D and E relationships which we will, some of them we will see in later parts of the course. Okay. Similarly, your B is related to H by mu 0 H for the vacuum case, and for the non-vacuum case it is very complicated, but one possible way of representing them is to write down with the relative mu r. Mu 0 is called as permeability and mu r is called as relative permeability, relative again with respect to vacuum. Okay. So, from the tables you can find out what is the value of epsilon 0 and mu 0. This is a small exercise for you, so that you can go back and take a look at your electromagnetic textbooks. Okay. Now that we have all these quantities, all these equations written down and the relationship between D and E vectors, B and H vectors known, we can now manipulate these equations and arrive at a very interesting equation called as wave equation, okay, which will then allow us to describe how waves can be expressed first in terms of either E or H, and how exactly this wave would propagate in free space, in optical fibers, wherever you want to. We will of course first restrict ourselves to free space propagation, okay, and then introduce what happens, then introduce boundaries and study how light behaves at the boundary, because that is the basis of understanding propagation of light inside the fiber. Okay. So, thank you very much. We will meet in the next module.